Alrighty, so let me finish up my creditless survey of integer factorization by telling you what people know about polynomial selection for the number field sieve. As always in integer factorization, the game is to make everything as fast as possible, and the number field sieve offers so many parameters, not just in the algorithms for detecting smoothness and linear algebra and so on, but in the choice of polynomial at the very beginning. There's so many parameters that it's actually a difficult computational problem to figure out the best parameters for the number field sieve. As a reminder of what the number field sieve does for today's perspective, well, it's looking at polynomial values. Last time I said the algebra of what's actually going on with those values, but for today, all we need to know is it's looking at values of a polynomial. It tries to find those, the values that are smooth. It tries to find smooth congruences and then multiply them together to form squares. But okay, for today, it's just there's some polynomial, which let me, to make this talk somewhat more concrete than the previous ones, take the degree of the polynomial to be 5. The number m that you write n in base m, remember the basic condition was f of m is supposed to be 0 mod n. M, let's say, is between n to the 1/6 and n to the 1/5, then if you write n in base m, with negative digits if you like, but you could just take f5, f4, the coefficients of that expression between 0 and m minus 1. If you write n in that way, n equals f5 m to the 5th plus f4 m to the 4th, etc., plus f0, where all the f's are between 0 and m minus 1. And then for various relatively prime integers I and j being positive, you look at I minus jm times a scaled norm of I minus j alpha, which is concretely f5 I to the 5th plus etc. plus f0 j to the 5th. Now, there might be some bad polynomials, there might be some bad m's, but basically every m you look at is going to succeed in factoring n. However, they don't succeed in factoring n at the same speed. If you change the m, if you change the polynomial you're using, then you end up with different sizes and different smoothness probabilities of the numbers I minus jm, the congruences, I minus jm, congruence I minus j alpha. In other words, in the smoothness of the values I minus jm times f5 I to the 5th plus etc. As an example, if you chose n to be my favorite test number to factor, 3141592653589793323. As I said, this is my computer's random number generator output. I have the world's best random number generator. You can take m to be 1,000, and if you write this number n in base 1,000, you get it's 314 times m to the 5th plus 159. I'm just copying segments of 3 digits from n. f5 is 314, down to f0 is 323. The number field sieve does succeed in factoring the integer n by looking at I minus mj, I minus jm, times f5 I to the 5th, that's 314 I to the 5th, plus etc., plus f0, that's 323 j to the 5th, for various i's and j's. However, if you change m, instead of taking 1,000, which is certainly a reasonable ballpark, if you change m into 1370, then what happens to the polynomial? If you write n in base 1370, a priori you would expect the polynomial to have coefficients between 0 and 1369, but in fact the coefficients are much smaller. The polynomial in that case, if you change m to 1370, the polynomial f5 is 65, f4 is 130, f3 is 38, and then 377 is the biggest one, 127, and 33. As you let I and j range over whatever reasonable range, the values here, the congruences, I minus 1370j times I minus j beta, those are more likely to be smooth than the original values, and the number field sieve correspondingly succeeds more quickly. When you're actually doing this kind of computation in practice, you look at a whole bunch of possibilities for m. Let's say you look at 2 to the 45, even more possibilities for m. So look at a whole lot of polynomials and feed them through some sequence of aborts. Say, okay, some m's, you look at them and you instantly see they're no good. They're not going to produce little polynomials. Some m's are okay, they produce polynomials that at first glance look okay. You look at those polynomials more closely, you identify, say, 2 to the 25 out of 2 to the 45, 1 in a million m's. You say, those are the best m's. And then, after I describe how we're going to look for m's, I'll talk about how you look more closely at an m and say exactly how good is that polynomial, which of those m's really is best. For the moment, let's just say to do an initial selection of m, to get a crude idea of how good a polynomial is, let's just look at the size of the coefficients. Where size can be scaled depending on how big your I and j are, in the middle here I've got if I is, well, you could say I is up to y and j is up to y, or in general there's a separate parameter r. You're sieving over r squared region of the ij plane, but you might have I being bigger up to s times r and j being correspondingly smaller up to s inverse times r for some parameters s and r. Then if I and j are in that range, you still have r squared pairs I and j, of which a large fraction are co-prime. And then, going off the right edge, the size of I minus jm times f5 I to the fifth plus etc. is at most just crudely bound the polynomial coefficients, scaling them by I and j appropriately. I've given a name here to the size of this bound for the congruences, for the numbers we want to have being smooth. Well, these are norms of the congruences. I'm calling this mu of m comma s times r to the 6. Mu of m comma s is basically m over s plus s. That's the size of I minus jm at most, times the sum of absolute values of f5, f4, and so on through f0, scaled appropriately by s. For an initial pass-through polynomial saying, okay, here's a bunch of m's, which ones are best, you want to find m's that make mu of m for some s be as small as possible. And that's a bound, which is, okay, later we'll look at how close that bound is, but for the moment, let's just assume all the I minus jm's times etc. are close to mu of ms times r to the 6. We want to optimize mu of ms r to the 6. If you didn't look at a bunch of m's, if you just chose a random m and didn't try to find the best one, then you might choose m to be almost exactly n to the 1/6, maybe a tiny bit bigger, and that would give you mu of m comma 1. If s is 1, simple case, then this bound is n to the 2/6. This is saying that I minus jm times f5 I to the fifth plus etc. is at most n to the 2/6 times r to the 6. And, well, that's clear. This is a polynomial that jm is at most, j is at most r, if s is 1, and m is at most n to the 1/6. And then the f5 I to the fifth plus etc., all of the f's are at most m. And the I to the fifth and j to the fifth and all the intermediate terms, those are at most r to the fifth. So overall we have r to the 6 times a couple of n to the 1/6. That's n to the 2/6, which is mu of m1 times r to the 6. How long does it take to do better? This is the baseline of trying 1m. You get a bound of n to the 2/6 times r to the 6. How long does it take to reduce that by a factor of 1,000, 1,000,000, 1,000,000,000, even more? Let's say a factor of b. How long does it take to find an m such that for that m there's some s where mu of ms is 1 over b times n to the 2/6? Say 1,000,000 of n to the 2/6. I'm going to give you several answers to that, increasingly fast answers. Let me emphasize before that the importance of doing this. If you have n to the 2/6 and replace it by 1,000,000th of n to the 2/6, that's like taking n and dividing it by 1,000,000 to the 6 halves. That's like chopping, what, 60 bits out of n? And if you can take b to be even bigger, then it's even faster. So this is like taking the number field sieve input and chopping 3 log b bits out of it. In general, well, okay, as the degree grows, the effect changes with d, but for a typical degree like 5, this is the effect. It's chopping about 3 log b bits out of n. You can, instead of looking at 2 to the 45 choices of m, you can look at, well, whatever you can afford to look at without really expanding the number field sieve time. It's not worth it to spend so much time looking at m's, to look at so many m's that, well, you end up with your number field sieve time dominated by the parameter selection time. But it's definitely worth spending, say, 1% of your time on looking for values of m. And depending on how long it takes to look at a bunch of m's, depending on how long it takes to find an m, where mu of m comma s is a millionth of what you would get randomly, depending on how long that takes, that tells you how long it takes to, what am I trying to say? However long it takes you to look at a bunch of m's to get mu of ms being reduced by a factor of b, that tells you how big b can be. In other words, it tells you how much reduction in the size of n you get from looking for better m's. The simplest thing to do, the easiest way to find a reasonable m, better than just choosing one random m, is just look at sequentially a bunch of possibilities for m. So you look at m near, for instance, the fourth root of b times the sixth root of n. And what happens if you expand n in base m, where m is about fourth root of b times the sixth root of n? Well, the leading coefficient is about n to the 1/6 divided by the fifth power of that scaling factor, the fifth power of the fourth root of b. So b to the minus 1.25 times n to the 1/6. And what about the other coefficients? Well, they're random numbers mod m, seemingly random. That means they range up to b to the 0.25, again, times n to the 1/6. Occasionally, all of those other coefficients are going to be on the same scale as f5. The goal here, if we want to reduce the mu values by a factor of b, mu is, think about I minus jm times I to the fifth times f5 plus etc. So think f5 and all the other coefficients have to drop by a factor of b if m didn't change, but m is increasing by a factor of b to the 0.25. So to compensate, to get overall a factor of b reduction in that mu function, you have to get all of the f's, all the coefficients of the polynomial reduced by b to the, 0.25 times b, so b to the 1.25 factor. And, well, sometimes that'll happen. F4, F3, F2, F1, F0, those seemingly random numbers mod m, sometimes they're each down to b to the minus 1.25 times n to the 1/6, which makes the mu values, makes the polynomial values a factor of b smaller than they would be otherwise. What's the chance of that happening? Well, each of the f's, if they were independent, uniform, random variables, then each one would have a b to the minus 1.5 chance of being below b to the minus 1.25 times n to the 1/6. If they a priori range up to b to the 0.25 n to the 1/6. There's 5 b to the 1.5 chances. Overall, that's b to the minus 7.5 chance of one m working. If you look through b to the 7.5 choices of m, then you end up with reducing the mu values, the polynomial sizes, by a factor of b. Which is certainly not the best we can do. Everybody's first idea is, well, you can easily just jump from one m, where f4 is small, to the next m, where f4 is small. If you start with, let's say you've just chosen a random m, and you look at n being f5m to the fifth plus f4m to the fourth, etc., then to improve that polynomial, if f4 is pretty big, you can say, wait a minute, f4 is not supposed to be bigger than f5, and I can easily just adjust m. I can add some k to m in such a way to make the fourth coefficient a lot smaller, on the same scale as the f5 coefficient. Specifically, if you take k to be about f4 over 5f5, then when you write n in base m plus k, I've written out the result there. N is f5 times the new m to the fifth, plus f4 minus 5k f5 times the new m to the fourth. And that f4 minus 5k f5, k is chosen to make that small. You can easily skip from m to an m plus k, where the f4 coefficient is on the same scale as the f5 coefficient. And then you just need the other random, seemingly random numbers, f3, f2, f1, f0, to all satisfy some condition that happens with seemingly chance b to the minus 1.5, and overall the chance of that happening is b to the minus 6. If you try skipping through b to the sixth values of m in this way, then you end up with, conjecturally, people try this in practice and all the randomness assumptions seem safe, you end up with the mu value reduced by a factor of b. You can do better by skewing the i's and j's, increasing that s. Instead of saying, okay, all the f's, all of the polynomial coefficients should be on the same scale, say, all right, let's change the scale. Let's have f5 forced to be really small. f5 is what gets multiplied by I to the fifth. So if we make I bigger and compensate by making f5 smaller, then we end up with polynomial values on the same scale. And it turns out that that skewing actually saves time in looking for the m's. Let's look at the exponents. If you, instead of have m near b to the 0.25 n to the 1/6, suppose you have it near b n to the 1/6. Then what happens to f5? Well, the scaling factor of b gets turned into the fifth power in f5. f5 is about b to the minus 5 n to the 1/6. Later, in order to have that f5 times I to the fifth, there's a b to the 0.75 down there, to have that look like the b to the minus 1.25 that we need. If you calculate the differences and divide appropriately, you get a scaling factor of b to the 0.75. Anyway, f5 is about b to the minus 5 n to the 1/6. And F4, F3, F2, F1, F0, those are random numbers mod m. If you force F4 to be small, skip again to a bigger m where F4 is on the same scale as F5, then F4 is not going to affect the bounds on the polynomial sizes. If you look at F5, I to the fifth, I being fairly big, I being scaled up, plus F4, I to the fourth j, I being scaled up, but there's only an I to the fourth there, and j is smaller, then F4 has less effect there than F5. F4 being tiny means the F4 term goes away. F3, in order for everything to be balanced, F3 has to be on the scale of b to the minus 2 n to the 1/6, which happens 1 over b cubed to the time, and F2 has to be on the scale of b to the minus 0.5 n to the 1/6, which happens b to the minus 1.5 of the time. Adding up the exponents, you see it's reasonable to expect the polynomial values to be b times smaller when the ij range is skewed, when i's are multiplied by b to the 0.75 and j's are divided by the same factor. It's reasonable to expect 1 over b n to the 2/6 for the mu values after only b to the 4.5 choices of m. One more step, the last step I'm going to talk about. Who knows whether this is the best, but it's the best I know. Gets b to the 4.5 down to b to the 3.5. This is all from the original, what was it, b to the 7.5. So b now gets to double in number of bits. Instead of chopping, say, 40 bits out of n, we get to chop 80 bits out of n. Depending how much time you're spending on the factorization, that tells you how big you can afford your b to be, but that's certainly affected by the exponent here. We've doubled the number of bits chopped out of n by looking for better m's. All right, how does this last technique work? Well, let's say, again, we have n written as f5m to the fifth plus f4m to the fourth, etc. To some extent, we can skip through m's that have not just f4 being small, but also f3 being small. If you like, if anybody's scared by tiny little formulas like this 10f5k squared minus 4f4k plus f3, feel free to assume k is 0. Feel free to assume you've already moved from m to m plus k, so that f4 is small. f4 is tiny on the scale of f5, and k is now 0. But L is important. I've written down a lattice here. Use standard lattice reduction techniques to find short vectors in this lattice. I'm going to retroactively show you where that lattice comes from just by asserting it's exactly what I need on the next slide. But okay, here's a lattice, a four-dimensional lattice. If you look at it, you can see it's not just a random set of vectors there. It's structured in a way that turns this into what people call integer relation finding rather than general lattice reduction. There's even faster algorithms than the usual lattice reduction algorithms for finding short vectors in lattices of this type. In general, your intuition about lattice reduction should tell you that it's easy to find some reasonably short vector in a lattice. If you want to find all these short vectors in a lattice, short being defined by how big the lattice is, if you want to find all the reasonably short vectors, usually there's not very many. And usually that's fast. Occasionally it's not, but, well, we don't need every possible m to be handled quickly, as long as they're handled quickly on average. If you have a short vector, look through the very few short vectors on average. If you have one that has a special form, has a v and v squared and a 1 in there, then, well, okay, you hope, just by looking, this is a very fast test, you hope that there is a short vector in this lattice which tells you a small integer v where 10f5k squared minus 4f4k plus f3, that first number, basically f3 if k is 0, plus 20f5kl minus 4f4lv plus 10f5l squared v squared, you hope that that ends up small for some value of v. And this is something, if you look at how big the lattice is, look at the lattice determinant, then you can see that this is a very fast computation using lattice reduction. And now instead of writing n in just base m plus k, skip by multiples of this L, L being m over 5f5. If v satisfies this condition on how small it is, then, all right, it's very easy to see that the f3, the new f3 coefficient, if you change from base m to base m plus k plus vl, it's easy to see that that degree 3 coefficient is somewhat smaller than it was before. The degree 4 coefficient, f4, you can easily make be on the same scale as f5. Now it's somewhat bigger, b to the minus 4, but that's okay. It doesn't affect the total size of the norms until it gets up to b to the minus 3.5. b to the minus 2 is the right size for the degree 3 coefficient. And then, well, the degree 2 coefficient is something seemingly random that you just have to hope is small enough. And overall, if you look through b to the 3.5 plus little o of 1 values of m, skip through that many values of m, then conjecturally, experimentally, you do find short vectors sufficiently often that you will find mu being 1 over b of what it normally is. All right, so you look through a whole bunch of m's, and you say, okay, here are the m's where the polynomial coefficients are smallest, so some bound on how big the polynomial values is smallest. But that doesn't mean that the actual polynomial values are smallest. And furthermore, smallest versus what do we actually want? We want smoothness of these numbers. Smoothness is affected by all sorts of number theoretic, well, arithmetic information at primes other than infinity. So what do you do to look at a bunch of m's and figure out which one really is best? There's this initial filter finding m's that are, spending a while finding, say, 1,000,000 or 1,000,000th of the m's you looked at initially, that are the best ones, that have the smallest mu values. That's a crude approximation to how good an m is. How do you then look through, say, 2 to the 25 m's and figure out for each one of those what the smoothness probabilities are? You might want to also vary y at the same time and try different possibilities for y if you don't have some magical far future analytic number theorist telling you exactly what y should be, rather than what analytic number theory does for us today, which is telling us it's something to the 1 plus little o of 1, which for sufficiently large numbers, that exponent converges to 1. Thanks. Analytic number theory is useful, but not when you get into detailed optimization. Sorry, any analytic number theorists in the audience. Anyway, so you have a bunch of m's, and you could see how good an m is by just trying the number field sieve for a little while. Try some random congruences, see how smooth they are, and, well, whichever m gives you smooth numbers the fastest, that's the best m. Keep going with that one to finish factoring n. The problem with this is it takes a while. Out of a given number of congruences, only a fraction 1 over y, roughly, only a fraction 1 over y of them are smooth. Y is chosen so that you write down something like y squared congruences, and only about y of them end up being smooth, even fewer. So you have to look through at least y congruences for one value of m, which is only a small fraction of the number field sieve time, but then you have to do it for a lot of m's, and you have to do it, say, 100 times, that, 100 divided by the probability of smoothness, to get a reliable estimate to figure out what the best m is. It would be nice to have something faster. It would be nice to have something where we can look at a lot of pairs m and y and say, okay, without having to run the number field sieve for a little while on each of those, here is the one that's going to be best. Here is the one that gives us the top smoothness chances compared to how big y is. As a first step in doing that analysis, let's see how many small congruences there are. You always choose some limit. Here I've called it h, height bound on the numbers that you want to have being smooth. The question is, for a given m, for a given polynomial, f5 through f0, and then given this h, how many small congruences are there? How many small values, I minus jm times f5 out of the fifth plus etc. are there? How many values, when I say small now, I mean between minus h and h. Nowhere near as small as y. Y is going to be, usually we have n as some big number, and then smaller congruences that we want to have being smooth, and then y, the smoothest bound, being even smaller than that, the usual 3 scales of numbers. Here I'm talking about smallness of the intermediate numbers, these norms, that we want to have being smooth. Certainly you could, in the number field sieve, look at all of the i's and j's up to some limit, but that would not be a sensible thing to do, because if you take a square or a rectangle of pairs I and j, the polynomial values there, I minus jm times f5 out of the fifth plus etc., are sometimes a lot bigger. In the corners of the rectangle, the biggest I and j, they're a lot bigger than they would be for some points outside the rectangle. The region of i's and j's for which I minus jm times f5 out of the fifth plus etc. plus f0 j to the fifth, the region of i's and j's for which that's below h in absolute value, is not at all like a rectangle. You should be, and in practice when you actually do number field sieve computations, you are looking at some more complicated region of i's and j's, and you could figure out how big that region is for given m and f5 and f0 and so on. You could figure out how big the region is by just looking at a bunch of j's and very quickly figuring out what the I range is for each j. Or, to save time, Remember that i's and j's all go up to about y, so you don't really want to be looking through a bunch of j's. Even statistically, looking at a fraction of the j's takes more time than saying, wait a minute, we're just computing an easy area. We're trying to figure out the area of the real plane, of the i's and j's in the real plane, for which I minus jm times f5 out of the fifth plus, etc. is below h. The number of integer pairs, number of lattice points, I and j, where you have some coprimality condition and they're inside this region of the real plane, is about the area of that region times some 3 over pi squared for coprimality and sign. So I've written down exactly what the area is. 3 over pi squared times h to the 2/6 times the integral of 1 over f of x squared to the 1/6, where f now, the big F, is the previous f times x minus m. This integral, well, looking at it for a moment, if big F were sufficiently small degree, this would be an elliptic integral. You could do very quickly with the arithmetic geometric mean. Even if it's not, well, all right, there's slight generalizations of the arithmetic geometric mean to genus 2. It's still reasonably fast. But once you get to sufficiently large degrees here I'm trying to integrate dx over y, where y to the 6th is the square of a degree 6 polynomial. So, I don't know, what is that, genus 50 or so. It's a big computation that you can't do with arithmetic geometric mean type techniques. I don't think anybody's even written down the formulas, let alone evaluated their cost. But you can do it with just ask a numerical analyst, and he'll tell you, wow, this is a reasonably smooth function, figure out the singularities, figure out what's happening at infinity, chop up the interval into reasonably small intervals where you can do the integral by power series, or Puiseux series. All right, and that's reasonably fast, almost as fast as the arithmetic geometric mean. An integral is very easy to evaluate. That tells you about, conjecturally, all of this is conjectural, tells you about how many lattice points there are in the region, the pairs I and j. All right, once you know how big the I minus j m times norm of I minus j alphas are, then next natural question is, okay, what's the chance of numbers that big being smooth? And I've already told you the answer to this. I've told you that numbers are smooth with chance about u to the minus u, where u is the ratio between the number of digits in the bound on the numbers and the number of digits in the in y, the smoothness bound. But that's not a very precise approximation. If you want a more precise approximation, then you can compute it with just a little bit more effort, and here's how. You just write down some Dirichlet series, which might sound like a royal pain because there's a whole lot of terms in a Dirichlet series, but let me ignore that for the moment. Suppose that we want, for instance, the integers between 1 and h that are 1,000,000 smooth. How many of those integers are there? Well, giving a name to those integers, let's say s is a set of 1,000,000 smooth integers, then the Dirichlet series, I'm writing this as x to the log n instead of the usual n to the minus s or n to the s or whatever you want. X to the log n is a power series variable. Add up for each n in the set of smooth numbers, 1,000,000 smooth numbers, add up x to the log n, and that's 1 plus x to the log 2 plus x to the 2 log 2 plus etc. It factors into local series for each prime, 2, 3, 5, all the way through 999, 983, biggest prime under 1,000,000. All right, this series does have a huge number of terms up to any limit. Say you wanted to know how many integers up through 2 to the 100 or 2 to the 200 or 2 to the 400. How many of those are 1,000,000 smooth? Well, you certainly can't just enumerate the terms of this series, but you can just slightly change the series so that suddenly it's a very easy computation. Taking a hint from the function field case where, hey, all logs of norms of primes are just in a very discrete, what does this mean? Well, there are very few different logs of norms of primes from function fields. And well, let's try to imitate that for the number field case. Instead of working with 2, let's work with 1.1 to the 8th power. I'm going to change all primes so that they're integer powers of 1.1. The reason that I do that is that when you multiply together lots of different primes, there's many fewer powers of 1.1 up to any limit than there are products of powers of the original primes. So I'm going to increase each prime. I'm going to increase 2 up to 1.1 to the 8th, and increase 3 up to 1.1 to the 12th. You can check that each of these is an increase. Increase 5 up to 1.1 to the 17th, and so on, all the primes up to 1,000,000. What happens if I make that change not just to the primes, but in the smooth numbers? I change 2 to the 5th, 3 to the 4th into 1.1 to the 8th to the 5th times 1.1 to the 12th to the 4th. I'll change every smooth number into some slightly bigger numbers, and let me give a name to the new multi-set I get. Let me emphasize that I'm going to count. There's lots of collisions now between these numbers. S bar is the multi-set of numbers obtained by taking smooth integers in S and replacing the primes by these slightly larger real numbers. Well, you can still write down the Dirichlet series here, and you get, instead of x to the log 2, you have x to the log of 1.1 to the 8th, and x to the 2 times that, and so on. It still factors nicely over primes with this slightly changed notion of primes. Looking at this series for a moment, I claim this has many, many, many fewer terms than the original series, because again, there's just powers of 1.1 showing up instead of arbitrary integers. If I give a name to x to the power log 1.1, LG here is usual log base 2. If I give a name to x to the log 1.1, call that y, then 1 plus x to the log 2 bar is 1 plus y to the 8th, because 2 bar was 1.1 to the 8th. And x to the 2 log 2 bar is y to the 2 times 8, and so on, y to the 3 times 8. And all of the primes, the slightly modified larger primes, turn into simple powers of y. X to the power of log p bar, or x to the k log p bar, is simply y to the k times whatever integer was used in defining p bar as a power of 1.1. All right, let me give names also to the coefficients of this power series, call them C0, C1, etc. This is a series with very few terms. Suppose I've chosen a bound here of 2 to the 400. How many smooth numbers are there up to 2 to the 400? A whole lot. You can't possibly write them down. But you can write down as a multi-set, just as a set with multiplicities, you can write down these C0 through C2909. There's very few terms there. The number of smooth powers of 1.1, well, okay, the number of powers of 1.1 that correspond to smooth integers up to any given limit is much smaller than the number of smooth original integers up to that limit. If, working from the middle here, if you compute this series mod y to the 29/10th, compute the product of these series out to a precision of 29/10 coefficients, in other words, you compute the coefficients C0, C1 through C2909, then that tells you exactly how many adjusted smooth numbers there are in S bar. And those adjusted smooth numbers come from, you take your original smooth numbers and make them all a little bit bigger. So that gives you a lower bound on how many of the original smooth numbers, S, there are. S has at least C0 plus etc. plus C2909 elements below 2 to the 400. The relation between the 2909 and the 400 being just 1.1 to the 2909 is about 2 to the 400. Similarly, at the same time, you get, for every smaller bound, you see how many elements S has up to that smaller bound, at least a lower bound on how many it has. But these are all very slight changes to the primes. There's only a slight difference between how many numbers S bar has and how many numbers S has. When people optimize smoothness detection using early aborts and lots of other ideas for how you can most efficiently recognize smooth numbers, smooth congruences, then you end up varying the notion of smoothness. You don't consider just, all right, we're going to look for every y smooth number, as we saw in talk number 2. You can adapt to all of that in your notion of smoothness. If, for example, you don't allow squares of primes, then you can just modify your Dirichlet series to throw away the squares of primes. Instead of 1 plus x to the log p plus x to the 2 log p, you just have 1 plus x to the log p and stop at that point. You can do the same change with the p bars, and if you do that, then you eliminate squared factors of p inside your smooth numbers. Similarly, more subtle change you can make is start with C0 through C2909. Think of those numbers, which you can compute as enumerating all the smooth numbers up to 2 to the 400. If you then multiply that by x to the log 1,000,003 through x to the log whatever this number is below a billion, then that's taking all the million smooth integers up to 2 to the 400 and then multiplying them by one prime between a million and a billion. And then you can truncate that series to see how many of those there are up to, say, 2 to the 420. This is exactly the kind of smoothness that you see in an early abort context. Of course, we're not looking at just uniform random integers. We're looking at I minus jm's and I minus j alphas, where the smoothness probabilities are very much affected by how many small first-degree primes you have. Well, small first-degree primes, same as saying small primes. If you have lots of small prime ideals, then you end up with larger smoothness probabilities than you would otherwise. And that's very easy to take into account in this computation. You just, instead of looking at primes of z, you look at primes of q adjoined alpha. All right, if you are worried about how close these lower bounds on the number of smooth integers are to the reality of how many smooth integers there are, then you can just compute an upper bound the same way. Instead of increasing every prime a little bit, you decrease every prime a little bit. And that gives you upper and lower bound on the number of smooth integers, or in the number field case, number of smooth ideals. If you decide those are too far apart, then you can change 1.1, make it 1.05, make it 1.01, whatever number you like, and you can therefore make the bounds as accurate as you want. All right. I'm going to finish a little bit early here. Once you've collected all this information about the distribution of smooth ideals, and you've collected all this information about, before I had the distribution of size of I minus j alpha, where it's norm, and I minus jm. Once you've collected that information, you just do a little integral of one against the other to figure out the smoothness chance of ideals that have similar size to the I minus jm's, I minus j alphas that you started with. At least conjecturally, and in experiments, these are kind of close. They're not exactly the same. It's not reasonable to conjecture that these are extremely close, because there was an effect that I mentioned in the first talk of if I minus jm has some small prime in it, and n, the number you're trying to factor, does not have that prime in it, then I minus j alpha will not have that prime in it. And that makes I minus j alpha a little less likely to be smooth. If I minus jm and I minus j alpha both have a prime in it, then n would have to. So the smoothness chance for both I minus jm and I minus j alpha is maybe a little bit less than the smoothness chance for just the random element of this product of number fields, q for the I minus jm and q adjoint alpha for I minus j alpha. But it's sufficiently close that if you actually do computations, I've done a few computations, and at this point I can say, yeah, it's pretty close. It's within a few percent, depending on how big the parameters are. I haven't done enough computations to say, yes, this is asymptotically, it's going to be 1 plus little o of 1 times the smoothness probabilities. But I'm sure it's much more precise than the u to the minus u estimates. Again, this is once you know once you've done that super elliptic integral, then you know how big the I minus jm comma I minus j alphas are, as expressed by norm. And by using the Dirichlet series modified appropriately, you know how big, you know what the smoothness chance is for ideals of any given size. And then it's just take those distributions, integrate them against each other to tell you the smoothness distribution of ideals chosen according to the distribution of the I minus j alphas. If you like, you can push the Dirichlet series technique further. You can, for instance, just look at principal ideals. That's maybe closer to the I minus j alphas, is if you separate your ideals by ideal class. But all the smooth ideals end up being very well distributed in ideal classes. It's not necessary to do that extra computation. All right, at the end of all this, you say, okay, here's the smoothness chance. These are what these calculations very efficiently tell you. Here's the smoothness chance for any given m. Here's how big the I minus jm, I minus j alphas are. And here's the smoothness chance of those numbers, assuming reasonable conjectures. Then, hopefully, the runtime of the number field sieve is monotonic in that quantity. There's much more to say about trying to estimate the time for linear algebra. Do you really need y over log y relations? Do you need y over log y smooth congruences? There's not too much that people know how to say about this. There's some computations that are possible, but it seems you can just estimate smoothness probabilities, and the best smoothness probabilities will give you the best runtime for the number field sieve. Having chosen the polynomials, you then have to ask my students how to choose all of the parameters. It's not just y, it's y and lots of early aborts, and how do you do the elliptic curve method? How quickly can you do smoothness detection, throwing away a lot of your smooth numbers, but still trying to get as many as you can per unit of time? Well, then you run the number field sieve and hopefully set some new records. Thank you for your attention.
For the polynomial of degree 6, limits, you had to adjust sort of the coefficients by hand to make them small. And if you took, so asymptotically, you would take a polynomial of much higher degree. Can you automate this process somehow, or do you have to sort of?
Certainly, all the exponents, like the b to the 7.5 versus all the b to the 6, b to the 4.5, b to the 3.5, and then all the b to the minus 0.25s that showed up. Yeah, you can easily say how those change as a function of the degree,
Sure.
And then
can you reduce them? Is the question.
Can you reduce? You mean asymptotically? Can you do better? I don't know. So this, let me rewind to that. Yeah, so this technique, controlling kind of two coefficients, so making the f5 be small by making m be big. You push up m a little bit, that makes f5 small. Making f4 small, that's very easy. Kind of controlling f3 at the expense of a little bit of f4 that doesn't matter for the final sizes. That's a little bit of control that, well, it's the best I know how to do. As you scale the degree up, the effect becomes, all of this is swallowed up in 1 plus little of 1 in the exponent. You chop some number of bits out of n, and well, you can easily write down an asymptotic for that by, instead of all these numbers like 3.5 are just simple rational functions of the degree, and once you've written that down, then you say, okay, the total number field sieve time is blah. If b to the 3.5 is going to be a little less than that, then b should be blah, where, again, you replace 3.5 by your function of the degree, and then that tells you how big b is, and you're taking away some number of digits from n. Also, the degree comes in there, and that tells you how many digits you gain by searching for m in this way. Is it possible to do better? I don't know. This is the state of the art, but finding a polynomial with as small coefficients as possible, and expressing n as a value of that polynomial. This is something where you can say statistically that most n's are going to need polynomial coefficients that are at least a certain size, but that certain size is substantially smaller than what we can do with these techniques. At least once n is reasonably big, all the searching you do keeps finding better and better polynomials. Maybe for n below, say, 512 bits, these techniques are sufficiently fast that they will find the best polynomials. But as n grows, there's clearly lots of room for improvement. So the question here again, for anybody who has any ideas, it would be great to have improvements. The question is, you're given n, and you want to write n as f of m, or it could have a multiple of n being f of m, but let's just say n is f of m, where f's coefficients are as small as possible. Or you can scale the coefficients as I did with some s. How small can you find those coefficients? It's really unclear. This is the best I know, but there's obviously not too much complication that has gone into this, and if somebody has another little idea, then maybe that could dramatically improve the performance of the number field set.
So you showed, in this case, d equals 5 for the degree of the polynomial, but just for curiosity, do you know what was the size of the degree of the polynomial for the latest factorizations?
Ooh, that's a good question. Offhand, I don't know how big the polynomial degree was. Certainly, a lot of cutting-edge factorizations have been done with degrees like 5 and 6, but eventually 7 is going to be the right number. I wouldn't be surprised if that recent factorization of a 664-bit number into 332-bit primes in only 5 times 10 to the 18 optron cycles, I wouldn't be surprised if that was degree 6, but offhand, I don't know. I would have to look that up on the web.
I'm curious about the Dirichlet series technique. Is there a theorem in there in terms of for any Dirichlet series you do something and you get some improvement?
Well, there's certainly, if you want to accurately compute upper and lower bounds, then yeah, for a broad class of series, it doesn't have to be just local, as illustrated by, you can sort of compute the series and then truncate at some point and then multiply by more series and truncate and so on. And you can model pretty complicated smoothness conditions in this way. All of the numbers you get at the end, well, there's the easy theorem that these are, what you've done by this technique is enumerate smooth numbers, except that you've adjusted them so that there's very few different sizes of the smooth numbers, and you can just count them much faster than writing them all down. The fact that you have a lower bound on your number of original smooth integers, that's the easy theorem. The fact that it's close to the lower and upper bounds you get in this way are close together, so the real number's somewhere in between, that's also pretty easy asymptotically if you apply, for instance, theorems of Hildebrand on how the number of smooth numbers grows. On the other hand, once you adapt these techniques to number fields, then the theorems just haven't been written yet. You would expect that similar asymptotics hold for how smooth numbers, if for instance you wanted to know, suppose you double smoothness bound, how does that, or rather you double the bound on the size of the numbers you want to have being smooth, how does that affect the number of smooth integers? Well, for the rational numbers, the theorems have been written down for a broad range of parameters. For number fields, presumably the same kind of asymptotics are true, but saying that we expect it to be true is a far cry from actually doing a 50-page proof. Aside from what we can prove, you can just do these computations and you see the lower bounds and upper bounds are close together. Certainly you can prove that as 1.1 converges to 1, well, as you replace 1.1 by numbers closer and closer to 1, your smoothest bounds will certainly get closer and closer together. But if you find they're too far apart, then, well, that would be interesting news, and figuring out what to do in that case is open.
Okay, any more questions? Okay, thank you for